Hey guys, today we're going to talk about electron configuration a little bit more, and we're also going to talk about these things called orbital diagrams. So where I left you guys off, you just learned about electron configuration. Let's take some time right now to kind of go over that. So here is carbon and here is silicon. What I want you to do is use your periodic table to figure out what the electron configuration would be. That's the 1s2, 2s2 type stuff. That's what electron configuration is. So go ahead and try that out. Oops. Okay, so we know that carbon has 6 electrons and silicon has 14. So our little exponents up at the top there, they should add up to 6 for carbon and 14 for silicon. Here's the answers that I got for both of those. So right away, you'll know if you're right or you're wrong. If you're not sure as to how I got these answers, I'm going to go ahead and explain them by using the periodic table method. So first, we're going to work at carbon. Again, we're going to rearrange everything on this periodic table. So we have a nice 2x7 S block, a 10 long D block, and a 6 long P block. Remember, S can fit 2 electrons, D can fit 10, and P can fit 6. Carbon is right over there, number 6 on the periodic table. So we are going to fill every single row in each block and then write those down. And that's how we tell what our electron configuration is. So we're going to start with 1s2. Then 2s2, just going right to left every time. And then we end with 2p2. So that's our electron configuration. For silicon, same thing, rearrange. And then it is 1s2, 2s2, 2p6, 3s2, and 3p2. That's kind of our final answer. Sorry, that red circle should be over by silicon over here. So you'll notice that if I move back a little bit here, carbon and silicon are in the same column, but they're in different rows. So that leads silicon to be a little bit bigger, but also you can kind of see what's similar. Oops, this should say 3p2 right there, as it does down here. 3p2 is the number we're looking for. Okay, yesterday we talked about this. The energy level is the first big number. The type of orbital is the little letter, and number of electrons in the orbital, that's the subscript, or the superscript number. And then also, if you want to pause the video and write down this electron configuration with barium, that's the longest one we're going to ask you to know. So if you just kind of like take it back a little bit and cut it off, you'll have every other electron configuration. For example, carbon's was 1s2, 2s2, and 2p2, which is kind of similar to the first numbers you see here. So if you take those first numbers, change the 6 to a 2 up here, and then get rid of the rest of the stuff, you'll have carbon's electron configuration. So that's kind of nice that there's only kind of one electron configuration you need to know, and that every other one is just like a shorter version. Kind of nice. Today we're going to talk about orbital diagrams. Orbital diagrams, you can't learn about these unless you know electron configuration, because they just show the numbers a little bit differently. So today we're going to be focusing on superscripts, the numbers up at the top. And what orbital diagrams do is they turn that number up at the top, the 6 in this 2p6, into arrows and boxes. So here's kind of what it all means. The arrows you see up here, that represents an electron and its spin. Spin is new, and we'll talk about that a little bit. Kind of the idea is, if you look over here, these 3 boxes all represent an orientation. So for P, remember how it's got a dumbbell this way, kind of right to left, and then it's got a dumbbell forward and backward, and then it's got a dumbbell going up and down. Those 3 dumbbells are each an orientation. So each one of those dumbbells here is represented just by a box, instead of a nice fancy drawing of a double dumbbell. And then 2 electrons live in there, but electrons are both negative. So in order for them to kind of exist in the same space, we notice that one spins one way and the other one is going to spin the other way. So one spinning like clockwise, for example, and then the other one spins counterclockwise. And that helps them just exist closer to each other, which is what we found. The important thing about this here, guys, is if you can draw 6 arrows in 3 boxes to represent 2p6, you're going to be fine. Lastly, 2p is the orbital's name. So this would be what you would write in place of 2p6. For s's, instead of drawing 3 boxes and a total of 6 arrows, for s's you would only draw 1 box, because s only has 1 orientation and can fit a maximum of 2 arrows in that one orientation. So another way of thinking about it is think about the maximum number of electrons an orbital can fit. So for D, that's 10. You're going to draw half that number of boxes and fill them in with arrows. So for D, anytime you see a D, you're going to draw 5 boxes when it comes to an orbital diagram. Okay, so here's an example of a 1s orbital, kind of what I was talking about before. Notice it only has 1 box. A 2p orbital, here there's 3 arrows, so 3 electrons. So this one would be 1s2. This 2p over here would be 2p3. And then down below here we have D. Notice how there's 1, 2, 3, 4, 5, 6 arrows. So this would be 3d6. Notice how these arrows kind of spread out. We'll talk more about why they do that in a little bit. But the important thing to write is up top here. S orbitals can hold 2 electrons, which means they have 1 orientation, so 1 box. P orbitals can hold 6 electrons, that means 3 orientations or 3 boxes. And then D orbitals, they have those 5 boxes because they can fit up to 10 electrons. So think right here in this box, you could squeeze 4 more in if you needed to. And that way each box has 2 arrows or 2 electrons. Okay, so what we're going to do is we're going to come back to the electron configuration for carbon, which we know is 1s2, 2s2, 2p2. And what we're going to do is we're just going to convert these subscripts into boxes as a way of drawing the orbital diagram. So here it is. And you'll notice that each S, the 1s and the 2s, both have 1 box to their name. And P here, even though I'm only filling in 2 arrows, I still draw all 3 boxes because P has all 3 orientations available. And then I spread out the arrows just because the arrows like to be spread out. We'll talk more about the specific rules for that in a little bit. For silicon, it's going to look a little bit bigger because the electron configuration is a little bit bigger, but we still have the 1s2, the 2s2. Here for our 2p, we notice that we need to fit 6 arrows in. So there's 3 ups and 3 downs in each one of the 3 boxes. 3s looks the same as 1s and 2s, and then 3p looks very similar to 2p here. Since we're only fitting 2 electrons in, we fill them in the first boxes and we space them out. Okay, so it's understandable right now if you have some questions about this, if you're not really sure how all the rules work. Just because I wanted to give you a visualization of what you're going to have to do, that was this slide. Now let's move into some of the hard and fast rules so you know how to do this 100% correct every single time. Then we're going to get to some practice. Okay, so here's the electron configuration for carbon. We've shown you this already. What I want you to notice is how I'm just writing the orbital diagram slightly below. And again, these exponents here, I'm showing them as arrows now instead. The number of the boxes will always stay the same. Cool. Here's silicon. Same thing here, just showing it a little bit differently. Again, they should say 3p2, not 3p6. I need to change that. But it says 3p2 over here, so that's all good. Cool. Okay, so here are some rules. The names of these rules aren't super important, but it is important for you to know what to do and what not to do. So you'll notice in this slide here, I have a little area of what will happen and a little area of what will not happen. This first principle is called the Aufbau principle. What it says is you fill from lower orbitals to higher orbitals. So I would write that down, Aufbau principle, fill from lower to higher orbitals. And then just know what it means is this example here. Notice how I first fill in the arrows for 1s, then I move on to 2s. In this other picture over here, you'll notice I skip 2s entirely and put 4 electrons or 4 arrows into 2p. From what we know about electron configuration, that's incorrect, right? We would never say 1s2, 2s0, and then 2p4. That would be an incorrect electron configuration. So Aufbau just kind of put that into a rule and made a bunch of money off of it, which is bum because I could have done that, you know. Moving on here, we got Pauli's exclusion principle. This says electrons have opposite spins. What that means for you guys is that arrows go in opposite directions. So you'll always have in one box an arrow pointing upward and an arrow pointing downward. You'll never have one box where you have 2 arrows both pointing upward, but what you could have, let's say you have, I'm going to draw a 2p box really quickly. So here's 2p. You could have 1 up arrow in one box and then one up arrow in a second box over here. That's something that can happen because notice these arrows are both pointing up, but they're not both in the same box. So this over here, let me just redraw it a little bit. I've got two up arrows now in the same box. That would not happen. That would be an incorrect orbital diagram for 2p up here. Great. Moving along here, we have Hund's rule. Hund says electrons will spread out when possible. What that means is if you have three p electrons, so 2p3, notice how they're all up arrows and they're all one per box. What you'll see, what you won't see, I should say, is them kind of packed together. Kind of the idea is electrons like their space. A lot like men in a bathroom, or like now with current social distancing practices. Electrons will also kind of socially distance from each other. Obviously, they don't do that, but, you know, or I mean, they don't call it social distancing. They just call it Hund's rule. Yeah, so that's a thing. All right, here we go. Phosphorus, we already have done this problem before where we figured out its electron configuration. What I want you guys to spend some time on now is to think, how would you change these exponents into boxes and arrows so that we can write an orbital diagram? Go ahead and take a shot at it. Okay, here below is the orbital diagram. Notice that we have two arrows per every single box. For P, notice that these three boxes are all connected to each other. That's important. You want your P's and your D's to have all their boxes connected. Otherwise, it looks like you just have a bunch of s orbitals. And then notice here, 3p has three up arrows. They're all spaced following Hund's rule. They all have at least one up arrow. None of them have a down arrow, so they don't worry about Pauli's exclusion principle. And then lastly, and most importantly, you don't notice that there are any blank spaces here. So Aufbau's principle is also followed. Okay, here's me just showing it again, except this time using the periodic table to kind of help you out there, and just kind of showing how each one relates. Again, this shouldn't be 3p6. This time it should be 3p3. Not bad on that. Okay, here's barium and its orbital diagram. I don't know. I just thought I'd do it for you. So once again, in the same way that like you could shorten any barium's electron configuration to any other element you need to use, you could also shorten this orbital diagram down to any orbital diagram you need to use. Cool. Okay, last thing I want to talk about is the excited state, and that is when we have a moment where we don't follow Aufbau's rule. So normally, this is what an orbital diagram looks like. We just did this problem with phosphorus. Notice how the arrows kind of all line up. They're all where they're supposed to be. This is the ground state. It's kind of the normal. Now, what I'm going to do is take this orbital diagram and just rewrite it based on an energy scale, which you see over here. So I'm just going to transfer the arrows over. So this guy over here is the same thing as the orbital diagram below here. I'm just making it look a little different based on energy. What you'll notice is that these other energy states like 4s and 3d remain unfilled. What we're going to do is we're going to talk about a specific moment where you give an atom enough energy to excite it. And what happens is an electron is going to move from a lower energy state like 3p to a higher energy state like 4s. Notice how it's higher in energy and also the number's bigger. That is what we call an excited state. The key to know here is that the excited state is temporary. So please write that down. Excited state, temporary. Okay, moving on, orbital diagrams. Here are two more practice problems. Go ahead and try them out. Here's the answer for boron. It's kind of bleak. We've got 1s2, 2s2, and then 2p1. So there's only one arrow and two empty boxes. That's important there. If you only partially fill a p orbital, if you only partially fill a p orbital in, you still have to draw all three boxes. Even though you might only need to put one arrow in one of the boxes, you still have to draw all three. That's just how scientists do it. Next one, we have barium's electron, or no, this isn't barium. This is, what is it? Nitrogen. Awesome. So this should say nitrogen. big capital N. And then once again, we'll notice that it's 2p and 3 arrows all up, following Hund's and Pauli's rule. Cool. Valence electrons are the electrons in the outer energy level. So in this case, we're looking at the highest numbers for our energy levels, which in this case is the 3, that 3 coefficient, that's the energy level. So we would say that we have 2 electrons in 3s and 3 electrons in 3p. So phosphorus in this case, as you can see here, has 5 valence electrons. That's one way to keep it in mind, to calculate valence electrons. Another way to figure out how many valence electrons you have is by actually just looking at the periodic table. So back over here, the first row, everything has 1 valence electron. In the second row, they all have 2 valence electrons. Helium has 2, by the way. So that's kind of an exception to the rule, again, because it partially kind of belongs in the second column, but also based on reactivity belongs in column 18. Column 13, you might think it has 13 electrons. Nope, it's got 3 valence electrons. Column 14 has 4 valence electrons. These are the outermost electrons. Column 15 has 5. Column 16 has 6. Column 17 has 7. And column 18, they have 8. We won't really worry about how many valence electrons the D block has in here. It's not necessarily important. We do say, for the most time, 2, but when we get into ionic bonding, we'll realize that these have different ways that they behave with electrons. They're kind of crazy and weird, so it doesn't really matter for the D block. But if you want to put 2 valence electrons, abbreviate that VE minus, you can do that. Okay, moving on here. Here's a question. Do you ever get tired of writing out the entire electron configuration for some of our large atoms? What about something like krypton or tin or xenon or barium? Notice how these valence electron, or these, not valence electrons, electron configurations are just huge, right? They're so big and kind of annoying to write that much like ink on one spot of paper. It turns out that scientists, being the lazy people that they are, also got tired of doing this. So they came up with a shortcut. Here it is. Anytime you're in a noble gas like krypton or xenon, instead of starting at hydrogen, which is the first atom, you can start at the closest noble gas that's smaller than the atom you're trying to find the electron configuration for. So in this case, tin, the next smallest noble gas is krypton. For barium, the next smallest noble gas is xenon. So you wouldn't put xenon for tin, even though it's a little bit closer. We kind of play Price is Right rules here, where you can't go over. So anyways, what you can do here is, instead of writing out this entire electron configuration for tin, is you can just take the stuff that's similar to the noble gas, which in krypton's sake is like the first anywhere from 1s all the way to 4p6. And you can just turn that into the word krypton in little brackets here. And then you just write down whatever is not included in krypton's electron configuration. So that's a really nice way to shorten and give yourself a lot less work. Here's the same thing done for barium. Barium, instead of writing this whole thing down, you could just write Xe and then 6s2. And that's a shortcut for the electron configuration. Kind of cool, huh? Okay, so here's me just showing the shortcut using the periodic table, right? So kind of the idea is, instead of starting at hydrogen, we're going to start at krypton, because that is the closest noble gas that's smaller than tin. Xenon over here is bigger. I've all kind of said this already, but this is just a little more visual, showing you with the periodic table. So this is all the stuff we would have to write down if we were finding krypton. But what we're saying is, instead of writing all this stuff down, the 1s2, the 2s2, the 2p6, the 3s2, just write krypton instead. Whew! Save yourself some time, you know? And then to get the last line here, that's where you have to write it down. And you would be doing this anyway, right? Notice how they match, the top one and the bottom one. So your final answer is KR 5s2 4d10 5p2, which is a lot smaller than this whole thing, right? Kind of cool. Here it is with barium as well. Again, same thing. We're going to go to the closest noble gas, which is xenon, 54 versus 56. It's the closest, smaller noble gas. And then we're going to just say all of this stuff over here. We don't have to write that down. So instead, we're just going to write down Xe. And then the only thing we have to add in this case is our 6s2. Kind of nice that we only have to write down bracket Xe and bracket 6s2. Kind of fun. Okay, these are some rules written down. What I want you to do is go ahead and try and figure out what the shortcut is for aluminum. Awesome. Hopefully you got these rules written down and you tried out aluminum. Aluminum, the closest one is neon. So what we would write down is, sorry about that. What we would write down is Ne in brackets and then 3s2, 3p1. That would be our shortcut for our electron configuration. Cool. You can go ahead and try these other ones if you'd like. Go ahead and pause the video right now. Here are the answers. And then below here for chlorine, you can also do a shortcut for orbital diagrams, which is going to save you a little bit of time. Cool. I hope that you guys got something out of this. Here's me just again showing you how these shortcuts work. The bottom row is new. Everything else you just shortened by saying AR. And then here's chlorine. Same thing. It's the closest noble gas, which saves us just a little bit of time. And here's the orbital diagram, shortened again. Okay, awesome. That's all I've got for you guys. Hey, have a great rest of your day. We'll see you all tomorrow.